Welcome back to the channel. This is Mr. Wong speaking. So today we're going to be looking at the 2007 HSC question, which is worth 16 marks. This is part of Module 5, Projectile Motion.
Now in the question you're given a little stimulus of the projectile falling over along the trail, and then it kind of launches itself at an angle of 0. So it has no vertical component, it only has a horizontal component in this case. So a group of students investigated in which ball bearings were released from various points on a ramp. The ball bearings rolled down the ramp to the edge of a table at point P as shown. Their ranges were measured. And so the measured ranges are given to you here. In question A, it says plot the data from the table and draw a curve of best fit. So it's worth 2 marks. So what they are looking for is an accurate plot. So that means try and do this with crosses. The reason being is if you do HSC, they do scan a lot of the papers, and if you can actually appreciate when you dot these lines here, it's not actually very easy to see once you've scanned it. So crosses usually better, and it also kind of shows the precise location of where you think the data points are. And then the last one is a line of best fit. And this line should go through the midpoints of all the lines of your data point, unless it doesn't fit to your trend. But let's get into that in a second. So I'm going to plot this out in a different color. And I'm just going to quickly run through this. So vertical height is 10, range is 32. So that point there. 20 and 44. 30 and 58. 40 and 66. So that would be this point here. Notice, as you can see, by doing it in crosses, I can actually get a pretty close point of accuracy of where all the dots should be on my graph. Whereas with a dot, if you kind of circle it around, depending on how you circle it, you might not get the center point. So that's kind of one of the other reasons why we use crosses instead of dots. 50 is 76. 60 is 82. And 70 is 87. So about that there. Okay. And so the next bit is to try and draw a line of best fit. Now, the line of best fit needs to cut through the midpoints of the dots. As you can see here, it looks sort of linear. It's not perfectly linear for sure, but we need to find a midpoint through all these dots. So I would say, and this is me trying to do it freehand because I can't actually put the ruler onto the touch screen because it'll stop me from drawing my line. It'd be sort of like that across there, somewhat like that. What you could also look into is, are there any outliers to your plot? And that would be so. Now, if you think there was any outliers, generally what you want to do is just circle it and just write outlier. And the marker would know that you haven't considered that as part of your plot. In this case, for myself, I haven't really considered that. So I've left it as it is and I just drew it through. But if you do draw this outlier sign and then just draw your line of best fit, then most chances are the marker knows that you didn't consider it when you were drawing it. So that should be okay. Do remember though, when you draw the line of best fit, that line should go a bit beyond the extremity points of your first and last point. Obviously do it in one go, not like what I did just there by adding it on, but that's kind of the idea that you have there. Okay, so question BI it says user graph predict the range of the ball bearing release from a height of 80. So this is kind of the reason why I would encourage you to try and draw the lines a little bit longer. Okay, so along there like that, because that's aimed towards telling you how far you predict, or what we call an extrapolation, how far you think it might go. So in this case, at a height of 80, it's roughly around that. Again, minusing the little bit of error. So according to that, the distance at 80 is about 94 centimeters. And then question 2, it says calculate the horizontal velocity of the ball bearing released from a height of 80 centimeters above point P. Okay, so that's what we need to do. So let's just have a look here. This is at the, well, let's just say up here is 80, or where's the vertical? Above P. Whoops. So release vertical above P. So that's 80 centimeters up here. Okay, the release point from here to here is 30 centimeters. And so the question you're trying to find is what is the horizontal velocity? So what is ux in this case here? Now I know that the predicted range in this case is 94 centimeters. So I'm stuck for time. I don't know what the time is. So that's what we're going to try and work out. Now how I'm going to work that out is very simple. This is the overall height difference that we have here. Okay, so the overall height difference, if I do this, Sy is 30 centimeters equals to Uyt plus half Ayt squared. Now Uy, that value is going to be 0. Now some of you might ask why, similar to what I said early on. You are firing this at an angle of 0, so Ux is maximum, Uy is 0 because it's directly parallel to the surface, so there is no vertical component to it. So maybe I'll just put it down back here. I know that Sy is minus 0.3 meters. I know that the acceleration due to gravity is minus 9.8 meters squared. So let's sub this in. Minus 0.3 equals 0, because that's the Uyt. So Uyt plus half Ay, which is minus 9.8, and then we have t squared. So what we need to do is move everything over. So minus 0.3 times 2 divided by minus 9.8 squared, and that's our time. So if I plug it into my calculator, the amount of time it takes for it to drop is approximately 0.247 seconds. Okay. Next bit I need to do then is find the initial velocity. So our displacement is equal to our horizontal component times t. So ux, to find that, is sx over t. Sx in this context is 94 centimeters, or 0.94 meters, and time is 0.247. So the answer we get here, the initial velocity, is roughly again to three significant figures, 3.8 meters per second. Or 8.1, sorry. So that's rounded off to 3 sig figs.
That concludes our explanation for this question. If you found this explanation for past paper questions useful, please give it a like and subscribe for future videos as well. Thank you.